Good evening mga Bisaya. So in this video, we will be discussing about this one, load path. So we are done with, identifying all the loads and then the framing plans. Now in every design, like before you start the calculation for any project is applicable for all projects, regardless of what type of structure it is or what kind of building materials. You have to have a load path identified in your framing. So this is basically identifying where the loads came from and then where the loads goes from like from the roof all the way down to the foundation. So that's load path. So basically in this, like this is the same building that we used in lecture 8. Originally, this was not supposed to be not part of the lecture series, but since it is like the last discussion was about how to like what to consider in steel framing and how to make it efficient, then I just decided, okay, let's just make it lecture 8, and then this video about load path will be lecture 9. Now, like I said, the first thing you have to do is to identify the load path. So that means, so if like for like this first part would be about gravity loads. So the the load path, you have to identify load path uh, for the gravity loads, gravity loads at the same time the lateral. So the gravity loads we are talking about, like, you know snow load, lid load, live load, collateral load. So all of these loads here, no, this one except the bonding load, except the wind and seismic, because those are lateral loads. So these are the gravity loads, this one and this one, gravity loads, and then the lateral loads, it's either wind or seismic. Now to identify which one, like, like your structural elements. Now we should start from the roof. So if example, this is your roof framing. So you will have, you know, you will have the gravity loads. If you have purlin, so basically if you consider snow load, so snow load will be on your roof panel. I have here prepared like a section. So this one. So if we zoom this out, uh, so for example, if this is now the roof framing here is different. You have roof sheathing, and then the roof trusses are spaced like really close to each other, like 24 inches on center maximum. But the way it is framed, for example, steel frame it is framed the same way we frame back home, where we have, so for example, this is your building, and then this is your trusses, it's supposed to be like that. And then you have purlins. So this is the same as a steel frame, like pre-engineered building, where you have purlins. And then you have your roof sheeting or your roof cladding. So the snow load, for example, if you have snow load, will be carried first by your roof sheeting. So if we do like a blow up, like say view of this Orleans here, so you will have the roof top cord, truss top cord, and then say for the sake of discussion, we'll just use like a wood frame. So this is your purlins, right? That's your wood purlins, and then this is your roof. Let's use this in different color. So that is your roof sheeting. Now your snow load, right? Your snow load will be first resisted by your roof sheeting. And then from your roof sheeting, it will be transferred to your purlins. So the purlins will have a horizontal, like a vertical component at the same time a horizontal component. And then this load will be transferred to the, now first for the roof sheeting. So it is transferred to the purlins, but the purlins has to stay in place. Then you have to provide like fasteners. So it will be screwed or nailed. It will be fastened to the purlins, right? And then now the load is from the roof transferred to the purlins. It will be resisted by both, or I mean, uh, it will be divided into two components, the vertical component and the horizontal component. Then you will have, you know, usually they will just have some kind of like a toenail. So it will be screwed or nailed that way, or sometimes you have some kind of like a an angle clip. And then since you will have, now we will discuss the lateral later, like seismic and wind load, especially wind load, because wind load is basically from the roof, and then seismic is just from the base, and then just the reverse from the base go to the roof and then back to the foundation. So now, or should we discuss all together like this? The wind load. So we'll just discuss again the wind load like at the same time. So that is the wind pressure, say that's going up, that suction. So this nail will be subject to shear from the gravity loads at the same time withdrawal or tension from the wind pressure. So that's why it is ideal to use a screw as fasteners for wood, because of course screw has a better withdrawal resistance than nail, because nail is smooth compared to screw. Now this angle can resist both, gravity loads and lateral loads, but most of the time what we do is we will have some kind of hurricane ties, Simpson hurricane ties. So let's try. So this is what it looks like. Say it's 2.5 a. Okay. So this one. So this will hold your rafters or purlins anchored to your main support. Like for example, if it's trusses, or this is, in this case, this is a rafter fastened to the bottom cord or top cord of your wall. So that's a hurricane tie. So you can have any other, other way of fastening it. But the important thing is you need to know, like, all the loads. So if you have wind pressure to you have uplift in this, even the sheeting or this roof cladding, it has to withstand all the loads. So usually manufacturer have a load table for these types of, say, if you use a 16 or 24 gauge metal roof panel, then it can withstand, say, the usual 40 PSF, snow load or whatever. So you have to have like a load table to determine what gauge to use for the roof. That's why when we size, or we size the purlins, or the in the roof framing, if you have to make sure that you have the load capacity of this one identified first or determined first before you size your purlins. For example, um, you space your purlins at 6 feet on center, and then you design the purlins based on the stability, but the roof cladding is not enough or is not sufficient to carry that that much weight. So all you have to do first is determine what's the maximum span you can have for the roof sheeting, your roof cladding, and then say your cladding at that part for that specific loading. Say snow load is say 40 psf snow load, then you will know that this uh, metal cladding or roof panel can only span up to say 4 feet. Then you will space your purlins every 4 feet. Otherwise, you will need um, take care. Or if you are using a particular gauge and then it's only good for 4 feet, and then you space by 6 feet, then the cladding, the roof panel already failed. So you have to check first that one. So from your purlins down to your top cord, and then of course your top cord going to this one. So it will be a truss system. It will be transferred um, to the supporting walls, or if it's a beam, then it will be transferred to the beam. So for example, this is your trusses. We will have like a blew up section of this part here, like a view. So it will look like, so this is your top cord, right? Then this is your ink post, and then you have your bottom cord. Then say you have your diagonal. Now in this way, you have a if there's a wood frame, then you have usually a double top plate, the continuous top plate. So it will be transferred from from the trusses. So you analyze the truss. So once you determine the reaction, you apply it will pass through the top cord, right? So, and then if this is beam, then of course it will be a beam, right? If that is beam, wood beam or steel beam, like that, then from the beam it will be transferred to the column. But since you have both lateral load and uplift as well for the trusses, then again you have to fasten this one. Is either you have some kind of an angle clip here again, or you will have hurricane ties. But I don't think you have hurricane ties directly to the steel beam. So all you can do is you will have some kind of like a nailer, like a wood nailer, before the steel beam here. So regardless of how you will connect your like structural elements, as long as you know how to connect its components so that it can transfer the load effectively from from the roof all the way to the foundation. Now, if this is a wood frame, I prepared here like a screenshot of our typical wood framing. So you will have the trusses here, right? You will have the trusses. So it will be carried by this top cord and then to the studs, whole studs. Now, if there is an opening, then you will have a header. So this is your header. Then you have your cripple studs. And then, so from the top plate down to the cripple studs, then from cripple studs to the header, and then from the header to the trimmer. So this is called trimmer, this one, the one directly supporting the header. So um, that's called trimmer stud, or sometimes some engineers call it gang stud. So it will be transferred to that one, and then from here down to the bottom plate. Now, if this is, for example, a second floor, like on this one here, so from the bottom plate, it will not be transferred to the king post. Again, like for the trusses, like this in this particular example is a floor truss. If we blow up this section here, so that it will look like so this is your floor truss. So this is your floor sheeting, and then this is your floor truss, right? That one, like that. And then this is your, bottom plate. This is your stud. And then this way you have your wood nailer. And then this particular section that is ICF. So you will have, insulation. And then this is your This is your what do you call this one? The concrete core. So now most of the time, these trusses are not designed to support additional load from the unless you clearly specify that this member will carry the load from above. But most of the time, that's not the case. So usually we will have some kind of it's called like rim board here. So there will be like a rim board that will carry the load from above. And then in this, like on this side, there will be it's called a squash block. Now, if you cut section, uh, looking at looking that direction, so this is your trusses. This is your trusses. This is your top cord. This is your weave member. And this is your bottom cord. Then this is your sheathing, right? And then you have your bottom plate. Now on each side of the truss member, you will have the squash block. So basically, this squash block it could be 2x4, 2x6, it depends. And then it will sandwich the trusses so that all the loads from above will not be transferred to the trusses but to the squash block. So this will function some kind of like a short column bypassing the trusses. And then this one is usually 1/16 taller than the truss itself. So if the truss is um, say 18 inches or 20 inches depth, then this squash block will be 20 inches 1/16. That's the minimum. And then because this one considers if the squash block what we call this one shrink. So if there is shrinkage, then at least all the loads will not be transferred to the trusses. It will be transferred from the bottom plate to the studs bypassing the trusses. And then of course from your walls, basement walls, then down to the foundation. Now for lateral consideration, like in this particular scenario here, what are the lateral loads involved? Now, for the walls itself, like in this particular walls, what's acting is the lateral pressure from the backfill. So you will have lateral pressure there. And then, so we will do that, we will draw that one again. So you will have your footing or the basement walls, I would say basement walls. This is your footing. And then this is your trusses, right? This is your trusses, and then this is your bottom plate here. Now you have a lateral force in this acting in this direction. So you have the lateral force. Now if that's the lateral force, now what prevents this footing from sliding because you have a reaction here at the same time a reaction here. So to prevent that, most of the time we will use the slab. So we will utilize the slab as the support for your basement laterally. Now at the top of your basement, usually we will have like in this particular application, in this framing, we typically specify a um like a like a strap. And Simpson has a product for that one which is called PWF24. So the specific application for that one is this like a basement. So PWF24. So that's the main purpose of that one. Let's see if I can find images. See it. I don't know if it's clear. Um, so basically, I don't know if it's clear. So this one PWF24. So what it does is, so since the force here, like lateral force, is acting that way, and then it will push the basement wall, right? So it is supported by this one, and then this part here will be in tension, and then pulling the whole trusses. Now, if you look at the 3D, if you imagine how it is transferred to back to the foundation, so this is your, for example, this is your, so this is your basement wall, right? So you will have something like that one, like that. Now, imagine, for example, this is the trusses are spanning this way, and then this is pushing this wall. Now, this wall will be, like I said, resisted by the strap transferred back to the floor trusses, like this one here. And then the floor trusses, the floor sheathing will act, this floor itself will act as a diaphragm. It will act as a diaphragm. Then all these forces you will have, so at the base you have a uniform load, right, to your base of your basement wall, and that is resisted by the slab. Now at the top, it is resisted by the flooring itself, the floor assembly. And then that floor assembly, that load will be transferred to this wall, this one, to the side walls. It will be transferred here, and then this side as well. And then this is acting now as a shear wall. So that's how it is being transferred. And then if the load is in this direction, right? If the load is in this direction, so it's the same application. It is transferred to the strap, and then from the strap to the joist assembly, and then your sheeting will transfer the load to this wall here, side walls. And then so that's basically how the loads are transferred. So from the roof, you have gravity loads down to the foundation, but your foundation walls have lateral pressure, which is going back to the floor assembly, and then from the floor assembly down to the what we call this one, to the walls. Now you now have, like, in this direction, you now have a lateral load perpendicular to the um, view, like perpendicular to the paper here. So in this direction, perpendicular uh, to this what you call this one, to this uh, surface. So to transfer that load to the foundation, so if this is your rim board, this is your trusses, right? This is your trusses like that, and then this is your sill plate, and then your ICF, you know, this concrete core. Now, to transfer that horizontal load is either design this, you know, rim board to resist all the lateral load because the sheeting is right here, and then you have nail like panel, it's nailing from your diaphragm design. So transfer this to the sill plate, and the sill plate to the concrete core. Or sometimes we will specify a framing angle here. So typically we use 835 framing angle. So it looks like uh, Simpson a 35. framing angle. So this one. So this is now the application. So you have the lateral load F1. So the spacing of this one is basically your total horizontal load divided by the capacity of this one. Then you have the number of angles required, number of A305 framing angles, or you can have any other connector, but we typically use this one. And then whatever is the number of um, angle connectors required, you divide that from the length, then you have the spacing. So that's how, like in wood framing, that's how it is. The load path. Now for steel framing, it is basically the same as the wood. In concrete, though, because the like I said, we already discussed like how like the floor framing for this one for wood and steel, where you have the you know you identify which direction your joist goes. For example, your joist is in this is head going in this direction. So basically, all your loads, like floor loads, are transferred to this one. But for concrete, it is two-way. Then you have the triangular and trapezoidal distribution. So this area will transfer to this beam, and then this one will transfer to this beam, and then this one here, this area will transfer to this beam, and then this area will transfer to this beam, and then you now have the concrete column. Now for lateral application, so you have this is your upper frame, right? So for example, that's your uh, roof frame, roof beams, and then you have your floor beams right here. So it's the same. Like for example, if you are using say like um what do you call this one hollow blocks or CHB walls. Now it depends. Like if your main attachment of your CHB wall is only at the top and at the bottom, and then here you have some kinds of like gaps or something. So all your like wind pressure to your walls will be transferred to the beams, the roof beam and the floor beams. Or if you want, you can assign, maybe half of the wall it goes to this one here. But all you have to do is when you model your what we call this one, when you model your frame, you have to identify which element supports what. So for example, you decide, for example, if this is a steel frame, right? So if it is a steel frame, usually we have girts spanning in this direction, right? So that means all the wind loads are transferred from your girts to the to the column directly, right? But if this is wood frames are framed like this is your studs. So this is your studs. Now your load are transferred not to the column but to the beam first, right? So it will be transferred to the beam first before it is transferred to the column. If that is a steel construction or um a wood concrete construction with what we call this one with like say metal stud infill, then that's how it is transferred. But if this is say if you have, for example, you assign this roof as a diaphragm. mm, if you assign that roof as a diaphragm, so therefore all the loads from your wall be transferred to your beam, but instead of to the column, it will transfer through your diaphragm and into these walls here. So that's why it is important to identify the load path before you even start your design so that you know where to apply the loads. So, for example, like I said, common back home, our common construction method is you have concrete frames, concrete Let's do again. So the common construction is you have the common construction is you have beams and columns. Now, if you are not using your roof, because usually you have your the way we frame it is you have your trusses like that one, assuming that's 3D, and some people even design this like a space truss. Regardless of what it is, your framing, you have to identify: are you using the roof as a diaphragm or not? But in typical construction, in back home, like in the Philippines, the roof framing are not designed as a roof diaphragm. Therefore, all your loads will be transferred to your beam first. So if you, for example, if you model in your model, if you apply the load at the nodes only, you are undersizing the beam because all the loads supposed to be passing through the beam first before going to the column. But if in your model you design it as a joint, or you apply it as a joint force right here directly without passing to your beam, through your beam, then you are undersizing the beam itself laterally. So this one, it's you design this by like for the gravity loads, that's fine. But when you apply the lateral load, if you apply this one to the joint only, like directly to the joint, then you undersize this one because it's supposed to pass through the beam first. Then the beam will have some kind of horizontal loading. So your beam will bend horizontally, and then you have reaction. So this reaction here, due to the lateral load, that's the load that you apply at the joint. So you have to be careful in modeling your frame, whatever software you're using. That's why there's a like a saying that in software that's garbage in, garbage out. Whatever you input, then if if your input is garbage, then your output is garbage. That's why it's important not only to know how to input, but or not to use not only to use how to use the software, but only to also to know how to apply the loads, because that's the most important. Because you if you apply the load correctly, then of course your result will be correct. So that's it's really important. It's crucial that you apply the loads properly. So like I said, if you're framing, if you have some kind of like metal stud, then it will transfer through the beam. But if you don't have a roof diaphragm, then it will act as a horizontal load to your beam, and then it will be transferred to this frame here. So if this is a rigid frame like a concrete column that can resist lateral load, then that's fine. If not, if this is a, say, steel frame like pin connected, then you have to have some kind of shear wall or a cross bracing in that wall. So that's for either steel or uh, concrete, and then wood. What else? Well, seismic. For seismic, it's the same. So remember, so for example, this is your frame again, and then this is two-story, for example. So this is your uh, like foundation. So your base shear is acting at the foundation at grade level, and then if you remember, we will transfer this load. We will distribute this load to the height, right? So you have if one and then if two. So there's a calculation on that one, and then you could probably have like if n. It depends. But the total, like all of this, if n, if two, if n, if present, if two, then if one, you add these three, then that is equal to your base year. Now, before you analyze this one, you transfer this load here. You also analyze that, you know, do we have some kind of like a what we call this one, how is it transferred? So the same as the wind. So you have to identify first, do you have like a roof diaphragm or a roof deck or a floor diaphragm that will transfer the load directly to the, because if you have, if this is, you know, if all the loads, this if n is basically based on the weight, the you have the wi h I, right? So weight at this level, eye level, and then the tributary height at that level. So this load, this if two is basically based on the load at, at your second level. So how is it transferred? So the same as the wind. Is it acting to the beam first, or is it acting through your deck as a diaphragm and then directly to the what we call this one, to the, is it like a shear wall, some kind of shear wall or cross bracing, or if this is like a concrete, that's a movement frame. So it's the same. Um, it's just the opposite. Like the wind load is usually applied from from above down to the foundation, but the foundation is, or the seismic is from the foundation, distribute that to its floor level, and then from the floor level back to the foundation. Now, uh, what else? Now for this lateral force resistance system, we will have this in a separate video. Although these here are basically related, but we will just discuss this in a separate video. So this one will just talk about the load path, and I think this covers everything when it comes to load path. Now all you have to do is basically identify where the loads like came from, and then where the loads are going. So from the roof, if you have a snow load, from the roof to your sheeting, then from sheeting to your purlins if you have purlins. If you don't have purlins, from the sheeting to the top cord, and the top cord to the wall here, and then down to the wall, and then to the foundation. And then if you have lateral load, it will be acting on your wall and then back to the floor level, and then your floor act as a horizontal beam like a diaphragm. Then it will transfer to the supporting to the side walls for like acting as a shear wall, and then transfer that back to the foundation. So it's more of like a loop, because it's, so for example, we'll draw another. So for example, this is a basement wall, right? So this is a basement wall. So you have lateral load acting on this wall, that one. So you have lateral load acting right here. Now, when the lateral load is acting in this, like say for the lateral earth pressure, it will result to a horizontal load at the top and at the bottom. Now this one will be carried by the floor diaphragm as a horizontal beam, and then it will be transferred to this wall as a shear wall. Now this one are subjected to horizontal load like a shear, no, that wall. So this wall is subjected to a horizontal load. But what's resisting that from sliding? Because the load now is horizontal, like the total load there. It will be now be resisted by this beam or this wall here. So it is resisted by that wall, and then this one will be pushing against the soil on the other side, on the back side, as like a, that's passive resistance. This one is active soil pressure, and this one is passive soil pressure. And then it will support the slab or the wall like a uniform slab, uniform support, like a spring support. And then this load here will subject this wall to bend in this direction. So if you look at the horizontal, like plan view, so this is plan view, so your wall or your load is coming from here, right? And then it is transferred to this wall here to the side, but it is resisted by this wall. And then this wall will tend to bend that way. Now, since you have you have active soil pressure in that direction as well, then it will do the same on the other side. So this will basically just cancel out each other. That's why it is it is um it is important to know also the grading of your property, because for example, what if in this particular example, so you have, you know, the grade here is, say for example, like that, but the grade goes this way, and this is like a floor level, now grade level. So in this case, you have a like a what we call this one, like a asymmetric load now, because you have lateral earth pressure in this direction, but nothing pushes against on this direction, like this direction. So you now rely on the frictional resistance of your building, or sometimes you will design this as a um, retaining wall with a keyway. So that's why sometimes you will see a retaining wall with cross section like this one. So this is your um, like wall. This is your footing, and then sometimes you have a it's either it's right here or sometimes right here. So this is your keyway, and this is the one resisting against sliding. So you will have a passive resistance there. So that's the purpose of that keyway. So you will see sometimes engagement calls this one. But if the backfill is, if the grade is flat, and then this is the same elevation, then there is no net sliding force. If this is at the same elevation, so that's fine. You don't have to worry. All you have to do is make sure that this floor truss is can withstand the compression. So this one will be subjected to compression, and then also the sheeting can resist the diaphragm action. So, like I said, in this scenario, since these are the same, like the backfill height is the same, so your net lateral pressure will be just the wind load. So just the wind. You don't have to consider this um for like overall stability of your structure, like primary structure. The overall stability, you don't have to consider the lateral earth pressure, because it is resisted by the same earth pressure on the other side. So you only have to consider the wind, because wind basically you don't um uh, i- the wind is in one direction only, so there's nothing preventing it from here, unless there's some kind of a, a support like a trace on the side, and that's another story. But as a, you know standalone building, if this is subjected to wind, then there's nothing that prevents it from sliding in this direction. That's why you have to design it for the net sliding force due to wind only, and or seismic, whichever governs. So I think that's clear already. So if you have questions, yeah, if you have questions, just uh, once I post this video, if you have questions, just you know comment, or you can send me like messages in Facebook. Then we will discuss that one, or I will answer your questions. So anyway, I think that's it for today. And again, don't forget to join our group, Structural Engineering for Dummies. So I invite you to join that group in Facebook, Structural Engineering for Dummies. And then that's for new engineers. So if you have questions, or for experienced engineers, if you see group members that ask questions, then if you know the answer, then please share your knowledge as well. Okay. Uh, thank you.